now that we're reading along, we get into a mathematical equation, and all of a sudden we're going to have to start doing math. So your textbook has what are called sample problems. Now they show you how to work your way through some of the math. And sometimes it's very simple and sometimes it's very complicated. But regardless, when you look at this whole picture, you just see formulas and you see numbers, and it gets to be confusing. So the thing to do is to cover it all up and deal with it one part at a time. So this is basically a tutor. This is, in your book, a homework problem, and then the explanation of how to do the homework problem. So this is example 4.1 in your textbook. And again, I'm not expecting that you can read this, but I expect that you can follow along with your textbook. And every now and then you probably hit pause and stop it and go ahead and do what it suggests doing. And maybe I went a little too fast because I've done it before, but you can certainly pause the CD or the YouTube or however you're viewing this. At any rate, we're doing 4.1. So we read it. It says a tractor pulls a loaded wagon on a level road with a constant force of 440 newtons. Figure 4.8. Okay, well at this point I'm going to go find figure 4.8. And there's figure 4.8. It says figure 4.8 right here. And there's a little wagon pulling a cart. It actually has everything listed. So if it wasn't for this figure, I would probably draw a picture myself. But there's one already there. But in my notes, I'm going to go ahead and do a little sketch of it. I'm not really big on wagons, so here's a wagon, and or a tractor, and here's a tractor pulling it. But the questions really looks like it's going to be interested in the wagon itself. So I draw myself a little wagon, and it's going in that direction. It's being pulled. So I got a wagon, and it looks kind of like that wagon. So now I go back up to my problem. And I go back and I keep reading. A tractor pulls a loaded wagon with a constant force. So there's a force of 440 newtons pulling a wagon. If the total mass, so the mass of the wagon, is 275 kilograms, what is the wagon's acceleration? And in this problem it tells me to ignore frictional forces. All right. Well, I've learned a technique for solving these kind of problems. The technique is to list my knowns in formula. Now, I've written them in this picture, but they were also written in this sentence. What I want to do is write them in some kind of form that I'm going to be using for a formula. So I know in my formula I'm going to use force to represent, or an F to represent force, and so I'm going to write an F here, and I'm told it's 440 newtons. So I've got that down. And then what else am I told? I read it. Now I know the mass, and in my formulas I'm going to be using the letter M to represent mass, and it's 275 kilograms. And then I'm asked to find acceleration, which is the letter A. So I've figured out that much. I think I've done that much. But let me look at my sample problem. The next thing it says to do is to think it through, and it says this problem is a direct application of Newton's second law. Note that the total mass is given, yeah, and when they treat the two separate masses, the wagon and the contents, as one. All right, so yeah, it says the mass and the contents. So I guess I wasn't even thinking about the contents. I was just assuming it was a wagon full of stuff. All right, so there it tells me how to think about that problem, and that's the way I was thinking. So that helps. So I'm on the right track. And then it says list the data, and it shows me a list of the data, and it says F equals 440 newtons and M equals 275 kilograms. So I don't need somebody to come along and say I'm doing this right. My book is telling me that I'm doing it right. Now, if I didn't do it right, if I had something else down here, what I would do is read what it says, write what it says, go ahead and write it down, and then start off with a new sheet of paper and start all over again. I would do it again because reading, thinking, and writing, three different parts of my brain. Just reading, only one part of my brain. So if you just read this, you don't learn it. You have to think it, then you have to write it. All right, what's the next thing to do? F is the net force, and the acceleration is given by equation 4.1. Okay, and I go back to my book and I find that equation 4.1 was the F equals ma equation. So here's my equation. F equals mass times acceleration. Now I've got to do algebra. Get a by itself, divide both sides by m to get a by itself. So F divided by m is equal to a. And so acceleration is equal to force, 440 newtons, divided by 275 kilograms. Now I'm going to have some problem with units here, but if I do this, acceleration is 440 kilogram meters per second squared divided by 275 kilograms. If I do my math, I decide that my acceleration is equal to about 1.6, and dimensional analysis leaves me with meters per second squared, which is units of acceleration. So this is how I think I should do this one. Now I'm going to go look and see what my sample problem has. Okay, there's the first one. They've done it. It says in case F equals ma, solving for the magnitude of a. So it doesn't show me how to do the algebra. I had to, oh that's right, that's why we spent so much time doing algebra at the beginning of the year. A equals F over m, I've got that. A equals F over m, I've got it here. A equals F over m. And then I plugged in my numbers just like it shows there, and then I've got the number here just like I've got right down here. So I see that I'm doing it absolutely correct. And then go to the next thing. The direction of the acceleration is in the direction the tractor is pulling. Note that m is the total mass of the wagon and its contents. The masses of the wagon and contents have been given separately. Say the mass of the wagon is 75 kilograms, and the contents is 200 kilograms, or vice versa. We would have added them together because the force is equal to this total mass times acceleration. All right, so they're kind of setting me up for later problems. That's why they're telling me this, because in a later problem they're going to give me two separate masses, but they're going to be connected together. So in the sample problem, they're preparing me to take this simple equation and make it a little bit more complicated. That's why I read it, and that's why I write it. So I'm going to write F equals sum of the masses times acceleration. So the sum of the force is equal to the sum of the masses times acceleration. All right, because that's what it says there. And there's also going to be a force of friction. So there's an effective force of friction of 140 newtons. In this case, the net force would be the vector sum of the forces exerted by the tractor and the frictional force, and the acceleration would be resulting. So now it's telling me if there was a frictional forces. Look at this. They're setting me up for a whole chapter on friction. So I read it here and I go, okay, acceleration is equal to force net, or the sum, divided by the sum of the masses. So it's going to be my applied force, 440 newtons, minus my friction force, minus 140 newtons. And because I've written it here, I can actually see it as part of my picture. So if I include friction, which I'm not going to do for another half a chapter, but it's already preparing me mathematically to do friction forces. So this sample problem is teaching me all sorts of stuff. Again, the direction A would be in the direction in which the tractor is pulling. With a constant net force, the acceleration is also constant. So the kinematic equations of Chapter 2 can be applied. Oh, great. Now it's going to get hard here. Okay. Suppose the wagon started from rest, so velocity initial equals 0. Could you find how far it traveled? X equals in a time of 4 seconds. And acceleration was 1.6 meters per second squared. Well, now we're already back to Chapter 2 questions. But yeah, I could remember that. A distance equals VIT plus 1/2 AT squared. VI is 0. Distance equals 1/2 AT squared. I've got acceleration. I've got time. I certainly could find distance. Yes, I could. So I go read the problem and use the approximate kinematic equation for the case. There it is. In your notes, it tells you distance equals VIT plus 1/2 AT squared. Distance equals VIT plus 1/2 AT squared. Okay. And so it's equal to 0. They just gave that value 0. I just eliminated it from the equation. But they 0 plus 1/2 AT squared, and it in fact solves for a distance. And had I plugged in the numbers, I could check to see if I was doing that all right. And there I've used my sample problem as a way to learn how to do all of these problems.